interval notation says it is all the things in between these two endpoints. You use a parenthesis when that endpoint is not included, where you go all the way up to it, but you never get there. Like, for example, if your graph went up to 3, but it didn't include 3, then that means it includes 2.999999, but not 3. You would put 3 here, but you put a soft parenthesis to say you go all the way up to 3, but you don't quite get there. You can't even list all the things. 2.9999, that goes on forever, but you never quite get to 3. If your point is included, then you put a bracket to say yes, up to 3, and including 3, and that's where you stop. Okay? And what you use on each side depends on this side. This is a bracket or parenthesis that goes with the smallest number, whether it's included or not. And this side is a bracket or parenthesis going with the biggest number, whether that's included or not. Okay? Make sense? Hopefully that's coming back to you. Hopefully it's not fresh, new, like you never heard that before. Okay? We're going to put it into practice now with some example problems. Okay? But going back here to the domain and range to start with, take a look at what this graph is showing you. That arrow on each end means that stuff is going on way off the graph it goes on forever. Okay? Now, unless that arrow is going straight up or down or straight left or straight right, if it's at any kind of an angle, whether a big angle or small angle, if it's at any kind of an angle, for example, this means it's not only going up forever, but it's also going to the right forever, and down forever, and to the left forever. Okay? So, even if you can't see it, even if it's off the graph, let's look at all these x values to the right. We're not talking about x-intercepts, but I'm going to follow the x-axis and think, is there any, this says infinite ordered pairs on this line. Will every single x be represented in some ordered pair on this line, even if I can't see it? Yeah. I mean, I could go over here to -5, and if x is -5, what is y? Well, I don't know, it's off the graph, but will there be one? Yeah. If I go to x is -5, I'm going to hit the graph if I keep going, which means there's an ordered pair on this line that is -5, comma, something. Okay? Every x in both directions will be in some ordered pair on this line. What about the y's? Is there any y that won't happen somewhere in some ordered pair on this line? If you go up and down this y-axis and you look left or right, you're going to hit the graph at some point. Every y value will be in some ordered pair. Okay? So we say the domain and range, and this is true for every diagonal line, okay, is infinite. Every x value is included. There are no restrictions on x, no restrictions on your domain. It's getting more algebra language there. In interval notation, what is the smallest value that x can be? Negative infinity, right? Now, we always use a parenthesis for negative infinity because negative infinity is not actually a number. You can never get there. It's more of a destination, but it's not. You don't get there. You just keep going and going. So we use a soft parenthesis. That would always, you never put negative infinity on the right either. Remember, this is the smallest, commas, biggest. What's the biggest possible x? Right, and close it with a parenthesis. Okay. And our range is also unrestricted. Any value of y will work for the range. Okay. Now, let's go back. Let's look at the rule, the relation. If I plug in x equals 1, for example, if x equals 1, what is y? Yeah, you can see that by plugging it in or looking at the graph. Is there any time I would plug in x equals 1 and get something other than 3? I reliably know that if x is 1, I'm always going to get 3. Is this a function? Yeah. You are always going to get the same y for any x you plug in. Now here's just a hint, don't write this down, planting the seed, college algebra. Not only do you have no repeated x values, which is what's required for a function, but it turns out every x you plug in is going to give you a different y. So you're not going to have repeated y values on this. Now, it doesn't matter if you did. It can still be a function as long as there's no repeated x values. But if there's also no repeated y values, it's a special kind of function called one-to-one. You'll look at that more in depth in college algebra. But we don't care about the not repeated y values right now. But the more you notice stuff like that, you start to be able to look at a graph and it starts to speak to you. So this is a function. Okay? Because when you plug in an x, you know exactly what it's going to spit out. It'll never be something different. There's no way 2 times 1 plus 1 is going to equal anything but 3, ever. Okay? thinking, by looking, like on the first page, by looking at the actual, and this is easier to do with discrete sets, looking at the actual x values, as long as none are repeated, you know you have a function. Okay. You can see that visually on a graph too. You can see it visually on this graph as well. You can see it by thinking just at the equation. You can look at that equation and think logically. If I plug in an x, do I always know I'm going to get the same thing? Okay. So those are some ways to tell if something's a function, by looking at the set, by looking at the graph, by looking at the equation. Okay. And the more you practice, the more you get better at that and becomes more natural. And there's some things that are always the same. For example, a diagonal line is always a function. It just is. Horizontal line is always a function as well. There's only one kind of line that's not a function. But let's show how you can test that, especially for ones that look a little wonkier. We use the vertical line test. Okay. So another way to tell if something is function, if you're looking at the graph of it, so this is a graphical or visual. Okay. So you have to look at a graph, a graphical or visual test. Okay. A graphical or visual to test if, I think I did some bad grammar there, if a relation is a function. Sorry about the bad Xerox there. If the relation is a function. Okay. So here's the idea. No vertical line, since the vertical line test, I'm going to abbreviate that, no vertical line drawn through the graph, abbreviate through, drawn through the graph, will cross the graph more than once. Okay. Yes?
You know how the problem did on the top left with the discrete points?
Yes.
It's you know how it's a segment, right?
Mm-hmm.
It's not a continuous, like, well, it doesn't go on forever even though.
Right.
Let's say, like, this one, well, let's just say the line, there was a line that went through every single point in between.
Mm-hmm.
How would we write the domain? Would it be how I said, like, -4 to 3?
If you just drew it from point to point without arrows coming out, so it stopped at those end points,
But it's a
Yeah.
line like this.
then it would include not just point, 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 but it would go from -4
Yeah,
to
it would
3.
include every single. So how would we write that?
We're exactly going to practice them just like that, but you would write it in interval notation, and interval notation goes from smallest to biggest. So the smallest element would be,
Yeah.
and the biggest, that. So it would be -4, comma, 3. And are -4 and 3 included?
Yes.
Then you would use brackets. Yeah, and we'll show some just like that. Yeah. Okay, so we're going to look at a couple of discrete ones and then look at some continuous as well. So these specifically right here are discrete, okay, both of these. Okay. So here's a relation. It's got 4 points. Okay. So, and same here. Go ahead and plot those 4 points on each of their things. Figure out what the domain is, the range is, and then we'll look at whether it's a function, specifically with the vertical line test. You can already tell if it's a function by looking at the list of points. But if you didn't have that and you were just looking at the graph, we can test that graphically, visually with the vertical line test. Okay, so first let's plot the points. Also point them here. So 4, 1. Okay. Discrete, point, point, point. No in between numbers, not connecting the dots. Okay. So here, either looking from the graph or from the relation list here with the 4 elements, what is the domain? -4. Okay. Yeah, and you can certainly put them in order if you like to. Absolutely. I'm just going to write them like I see them, but if you put them in order, that's great. It actually helps the eye see it. Or you can just write them as is. It's a short list, so really either way. It's not required to be in order. but it certainly is sometimes helpful, but either way. So if you wrote yours in order, that's great, no problem. So there's 4 elements in the domain. Are any of them repeated? No. So you can see that if you're given the points. What's the range? 9, 3, 4. Right. Now, if you have a repeated value, don't write it twice. Or 3, however many, just write it one time. 9 is in the range. We don't have to write it how many times it appears. It's just in the range. 9's in the range, and 3 and -5, yeah. And if you put that in the order of -5, 3, 9, great, no problem. Now, is it a function? Yes, and you can see that they're saying no repeated x values, but here's how you use the vertical line test. I like to use it, the idea is if you draw a vertical line through any point of the graph, so I like to take like a straight edge and just slide it from left to right across the graph. And whenever I hit the graph, oh, there's the graph, it cannot hit it more than once. Okay? So I know when I'm at -4, the only possibility is that 9. If it hit the graph somewhere else, there was another point, then that means that the x value is repeated. It might be this, it might be that. So the vertical line test visually lets me see, as long as the graph is never touched more than once as this slides across. Okay. What about here? Does it pass that vertical line test? No, I slide it across, and there's, when x is 4, it could be this or it could be that. That it hits the graph more than once. Doesn't matter that it happens twice. As long as it does it at least one time, it's not a function. Okay. So our domain here in this, the domain here in this one is? There are 4 points, but only 2 elements in the domain. And the range? And function, yes. Function, no. Okay with that? Okay. We're going to move into continuous then. These are both discrete. And now we're going to hone in more on the continuous, the ones we're going to spend more time with. Okay. So these examples right here are all continuous. Okay. Now, continuous doesn't mean necessarily they have arrows going off into infinity. You can have infinite points in between, even if it's what's called bounded. Okay? For example, this one doesn't have arrows, it has endpoints. But it's still all those infinite in-between points because the dots are connected. So that is continuous. You can't list all those individual points. Okay? Same thing here. This doesn't even go off in any direction. It's a closed loop. Okay? It's still infinite and continuous. Okay? All right, so we've already looked at a diagonal line, for example. All right? And saw that going off into infinity, both left and right and up and down, gave us an infinite domain and an infinite range. Now, knowing what we know about a line, but we can also test it with the vertical line test, and it passes that test, and it is a function. All diagonal lines are functions, and all of them have unrestricted domains. Okay. And this is, just to get some of that language in there, we know this is linear, obviously, because it makes a line, so it's in the linear family. Our next example here is a parabola, which puts it in the quadratic family. Now, as we get to some of them, sometimes it's hard to visualize this, some are trickier than others. So this is, I'm going to mark this up in a way, hopefully will be helpful. For your domain, you're thinking x values. Remember, this is not about x-intercepts. It's not about where it crosses the x-axis. You want to look at where it ends. There are arrows here. And those arrows are not going straight up or down. They're going at a slant. So it is getting bigger and bigger, bigger, obviously, as it goes up. But it is also, a parabola spreads infinitely. Okay? Way off the graph, but it's just never going to stop spreading right to left as well. So what is the smallest possible x value that will be represented in some ordered pair on this parabola? Yeah, negative infinity. It's all the way to the end. You can't even, it keeps spreading. You go to any x value, and if you go up, you're going to hit the graph at some point. Okay? So I'm going to represent that here with one color, going on forever to the left and forever to the right. Okay? So that visually represents all x values are possible. There's no restrictions on x values. Any x value is okay. There's no breaks, there's no jumps, and any x value is going to be in some point because I can go up and I'll hit the graph at some point because it keeps on going. So our domain is, like the line, infinite and unrestricted. Now, it's easier with a horizontal to think reading left to right. You always, for interval notation, you always go smallest to biggest. You've got to remember with the y-axis being vertical, smallest to biggest means going from the bottom up. Okay? Now, some things, like the line, will be infinite, top to bottom. Others will start infinite and then hit a bound. Others will start at a bound and then go up to infinity. And others will be bound at the bottom and bound at the top. Okay? So you got to be careful about that. Look, what's the smallest possible one, and move from bottom to top. What's the small, looking just at this y-axis, what's the smallest possible y value that will be in some ordered pair? Yeah, you're not going to see any negative y values, because if you go to any of those negative y values, move right or left, you'll never hit the graph because it's not there. So we start here at 0, and it keeps going on forever. Okay? So our range from bottom to top, the smallest value is 0. Now, is 0 included? Yes, it is included, so we use a square bracket, because the point 0, 0 is on this graph. And then all other y values, all other positive y values are represented, so it goes to infinity, which closes with a parenthesis. Function? Yes. And it can visually pass that vertical line test. When you slide this along, it's only ever going to cross the graph in one place. Now this one is bounded. Now it doesn't go off to infinity in either direction. It's got endpoints. But still, if the dots are connected, it is infinite. We're going to use interval notation. But it's bounded left and right and top and bottom. So you want to, on the x-axis, visually, what is the smallest possible x value that will be represented in an ordered pair? Yeah, and nothing below that. And I can keep going. There's no breaks, there's no jumps, there's no gaps until I get to what x value? Yeah, nothing bigger than 5 will be in any ordered pair, x in any ordered pair on this graph. So is negative 3 included? And positive 5? Yes. And for one like this, you tell that because that circle is a closed dot. And I'm not going to give you anything other than that now, but you will see moving forward in college algebra, an open circle would mean it goes almost there, but it doesn't include it, and you'd use a soft parenthesis if it's an open circle. All right? But with a closed dot, it is included. And that's all I'm going to give you right now. So our domain goes from smallest to biggest, and both of them are included, so 2 brackets. What is the smallest y value that will include in any ordered pair on this graph? Yes, anything below that will not be in any ordered pair. You will not see negative 3 in any ordered pair for y on this graph, for example. And what's the highest one? 4. And there you go. And that is bounded. I didn't draw any arrows. My range is always smallest to biggest. Be careful about this bottom to top, negative 2 to 4. Function? Yeah. Even if something's really steep, you can see if a curve is intended. Okay, so even if it's really steep, visually you have to be careful about that. No, it is curving. It's not just a straight vertical line. So it does pass that vertical line test. There's one like this on homework, and it's the same idea of this. It's bounded left and right, and it's bounded top and bottom. So I'm going to skip this one. I just want to make sure we get to everything, but I'll have this filled out, and you can check yourself later. Like I said, there's one just like it on homework as well. And it's the same idea as this, even though it's a closed loop. It has bounds on left and right and top and bottom. Okay? So let's look at this one, the hyperbola. That's the conic section, very important post-algebra, the conic sections. So this one's got a little trickier thing going to it. Again, first you want to think x-axis left to right. And those arrows, even though this is a pretty shallow curve, is it a straight up and down arrow or a straight left and right arrow? Or is it kind of curving? It's curving. So not only is it going up forever, but it is also, it's going down forever and left is spreading out to the left and over here to the right. Up and down forever, left forever, and right forever. But what about this? If I, for example, had x equals negative 1, and I go up and down from -1, will I ever hit the graph? No, because they're curving outward, and that leaves a gap. You will not find any ordered pair on this graph that includes 1 in the ordered pair as the x, and so forth. So think left to right, the smallest value is what?
Negative infinity.
Right, because that arrow says it keeps spreading. But it only goes up to -2. Now there's still more to this domain, but it takes a jump. It has a gap. None of these in-between ones, if you go up and down, will hit the graph. So where do I start back up?
2.
To infinity.
How can you put the U in there?
That's where you put the u, exactly. This domain has 2 intervals, but they're all part of the same domain, so we glue them together with the u. The first interval, always going smallest to greatest, starts at -infinity, goes up to, includes -2. Then we take a jump. None of these in-between x values are included in the domain, but I put a u to say union. You know, I'm not done yet. We're going to start back up at and including, and then go to infinity. And the range, right, every y value will be represented there because it goes up and down forever with no breaks. So -infinity to infinity. And is it a function? Yeah. It's a very shallow curve, but it is curving, so your vertical line will go through the graph in more than one place. For example, x equals -3 has a y there and a y there, repeated x value. So no. Okay, so there's diagonal lines, horizontal lines, and vertical lines. And this is a little special exception too. Just like I want to show the gap one, let's take a look at this. Let's just think domain. -2. Anything else? Yeah, this is actually just one number. It's not a whole interval of numbers. In fact, that's the very definition or the name of this vertical line. We know this is a vertical line when we see the equation because x equals, and it doesn't matter what y is. There's not even a y in here because y could be anything. It doesn't matter what y is. X will always be -2. That's what defines this vertical line. And that's in that graphing handout too to review horizontal and vertical lines. So the only thing that x is by definition is -2. Because that's just, do we need an interval for that? No, we could just say -2. So we're going to use set notation. This is just a single number. There's no small and big. It's just one number. The range, on the other hand, yeah, every y value will be represented in some ordered pair. And the horizontal line has the same idea, but reversed. You may see one like that on homework. Now, is this a function?
Yes.
All lines are functions,
Not vertical.
except vertical lines. Does it pass the vertical line test? Yeah. See? It can't because it is a vertical line. Every point, yeah. That x is -2. It's repeated in all those infinite points. Yeah. Now, horizontal line's not a problem. Diagonal line's not. But vertical line is not a function. It is a relation. It is graphable. It's a real thing. It's part of the linear family, but it's not a function. And there's several of this. There's a good amount of practice on this, on the variations on this on the homework as well. Are we okay with it so far? Okay. All right. I'm barely ahead. Lot to cover. But do interrupt me if there's a problem. All right. So sometimes you just have an equation. Okay. Here's a visual way, or you might see the list of a discrete set, ways to tell things are a function. Here we've got some equations. How can you tell if a relation is a function just by looking at the equation? Okay. All right, well, one way is to sort of think of it logically, like we did that diagonal line, and think, well, if I plug in x, am I ever going to get anything? If I plug in x equals 1, will anything ever happen but 3? Well, and y equals 2x plus 1, no. If you plug in x is 1, y will always be 3. You'll never get any surprises. Okay? So you can start to think logically about equations like that. Let's go a little deeper into that. You can tell by asking this, will, not sort of the logical thinking first, and then I'll point out some really specific cases. Will any x value occur more than once? course, if it will, then you don't have a function. And sometimes that's easy to see logically, like with a line, and other times it gets a little more complex, but we're going to look at some good clues for that. So, here is a quadratic, not linear, it's got a square, so we know it's going to make a parabola. Okay. This is also quadratic, so it'll make a parabola too, but look how the x's and y's are flipped. Okay. So that's going to make some difference. Let's make a quick table of values. Okay. Since we're solved for y here, then it's easiest to plug in x values. Now, remember with a parabola, the x values are unrestricted. You can plug in any x you want. Okay. Just to be easy and be consistent here, let's do -3, -1, 0, 1, and 3. I know those will all fit on the graph and it'll give a good illustration. Okay. Now, we're going to have a whole unit on radicals, which includes our exponent rules. Be very careful. This is why I always say, always when you're plugging something in, plug it in parentheses. So this is -3 squared. What does that equal? Positive or negative? Positive. When you plug in an x, you should always plug in what you're plugging in parentheses. And parentheses, and then one of the reasons is because if you've got exponents, parentheses make all the difference for exponents. Because the base is what's in parentheses. This is, in parentheses, it's -3 times -3, which is +9. Okay. If you don't put parentheses, then that negative is not touched by the exponent. It's just 3 squared, which is 9, and then it's -9. Parentheses matter for exponents. And you always plug things in parentheses. This is -3 times -3 is 9. -1 squared, 0 squared, +1 squared, and 3 squared. So you see we got some repeated, you plug in -3 or 3 and you get +9. You got some repeated x values. Throw that on the graph real quick. Connect the dots. We have our parabola. Even hand drawn, which can look a little wonky, like would that pass the vertical line test? Well, you know a parabola will. It is arching out and up continuously. So this is a function, right? It's very much like the one we have up here. Yeah. So yes, this is a function. Okay. You can see it visually with the vertical line test. You can see it from the table of values that none of the x's are repeated. The fact that it is solved for y is another clue. Now, you can solve things for y, but I'm going to show you when that's not a case, because sometimes it's very awkward to solve things for y, and they give more than one result. In this case, you're just given y equals, and then the stuff that's going on is happening to the x. If the y is free and clear, it's a good guess that it's a function. Okay. Here's the problem, though. Let's look at where these are reversed. X and y. Now, because we're solved for x instead of y, it's much easier to plug in y values. So let's plug in the same values, but for y instead of x. Okay. Because we're solved for x, now we're going to take that y, -3, and square it. Okay. So -3 squared. Plug in -1 for y, -1 squared, +1, and so forth. Any problem with the x's? Yeah, they repeat. So you know you're not going to have a function by that. Also throw it on the graph real quick. 0, 0. We've got 1, -1, and also 1, 1. And we have 9, 3, and -3. It's still a parabola. It's in the quadratic family.